Lecture number 5. It's time to develop Chern-Weil theory. We will write a bunch of formulas. I will try to be as clear as possible. We discussed what is a principal bundle. The connection is the collection of one forms Well, sorry, A alpha. One form on trivializing chart U alpha with values in the Lie algebra G. The relation between these two things on the overlaps should be given by the following formula. A beta is equal to G beta alpha, A alpha, G beta alpha minus 1. For a while, we can think that G is just GLR of, here we write the field K, real numbers or complex numbers. Then G is just matrices. But a little bit later, then we need to describe collection of characteristic classes. We will need to make this group more or less specific. For a while, it doesn't matter. So, what is a curvature? Curvature. We apply for two vector fields on the base and the section of our vector bundle E. So let me remind you that then we spoke about principal bundle and vector bundles. On all cases we had gluing a cycle. So I will define curvature in terms of for vector bundle, but we will see that formulas which we will obtain are valid also for principal bundles, because then we get rid of this section. We will see that the formulas are defined only in terms of gluing a cycle and connection form A. So what is it? We take a couple of derivatives in this order and in the reversed order, and then we subtract this expression. There was a problem for homework, very simple, that this object is obviously k-linear in 3 arguments. So if you multiply psi or e eta or section by a scalar, just by a number, then nothing happens. You can move the scalar outside. But it was the exercise that it is. We had an exercise, not very difficult, but nevertheless. F psi eta S is linear in all 3 arguments over smooth functions on the base. It means that if you multiply any of these things by a function, then you can put this function outside. I will write the formula. It's a kind of exercise for sure, because if you put f in some place here, then you need to take a derivative of the function f, and you need to check that there are no derivatives of f after final simplification and blah blah blah. So knowing that this is linear over the functions, we can think that curvature f is two-form on B with values in endomorphism of vector bundle E. Or if you want to think about this object as object with structure group, you will see that you can think about f as a two-form with values in the algebra D. Let us write some formulas for f in local charts. It will be very, very interesting. So we want to obtain a formula for f in local charts. Every time this is very unpleasing exercise. For me, it was unpleasing. I don't know how it's for you, but for me it was unpleasing. So I wrote everything explicitly for you. So, nabla is a sum of usual differential with one form A. So A can be written in coordinates as EI dxi. X coordinates on the base B. Okay, very good. So if I want to calculate the components of f, I need not to put here some arbitrary vector fields, but I will put here basic vector fields. So I want to calculate what happens if I substitute here di, dj, and apply it to s. To be clear, di is d over dxi. It's vector field on the base. So, if you, very important someone is left on the blackboard. If you speak about coordinate vector fields, there are no commutator. This thing vanishes. So we have here commutator of two partial derivatives with respect to basic vector fields and commutator applied to S. Okay. Minus something which I don't want to write at this moment. Is it okay? So what I did, I applied here covariant derivative with respect to the vector field J. So this is a differential of S. And here we see, is it correct or not? I can write a bunch of formulas, but some of them are correct, some of them are not correct. What I am doing here? It's incorrect, but we need to understand why.
What is A between this J?
So A is a one form with values in the matrices. So AI is a matrix and dxi is one form. So this is a basic one form. This one is a coefficient which is a matrix. No problem. It's.
Well, I think the second sum is correct, but the first one.
This is the thing which I want to calculate. This is correct because commutator of these two things vanishes. So there are no mistake here. So if I claim that mistake is somewhere, then either the statement about mistake is wrong, either mistake is here.
Mistake is here.
Well, okay, where is it?
We need to calculate commutator.
Well, minus blah, blah, blah. That's okay. You know that I will write something, then I interchange the indices, and I will not calculate the second part. The mistake is somewhere here.
For me, DS doesn't seem right.
Why? Yes, that's the correct answer, because we should pay attention to what we're doing. Either we do this operation, or we calculate partial, or we take a covariant derivative along vector field. This thing contains differential. This thing contains differential, but with psi substituted inside. That's why I will write. So if you substitute into the differential this thing, what we will have? Partial derivative. di with, so if you calculate ds and substitute there di, you will obtain just partial derivative of the section S along vector field, basic vector field. So here we have, so this is a correct, but this is a nabla, just covariant derivative in general understanding. So it's a section from one vector bundle to sections of another vector bundle. But if we take this guy, it is calculated by substituting psi into these things. So that's why here we have not A all summons, but only AI, because I substituted here basic vector fields d partial di. So everything vanishes except this thing. Well, so here we also write correct formula dj. Now we are fine, and we can calculate what happens here. How many summons we will obtain? Just to keep you in tonus, I'm asking you a very stupid question. How many summons will... Huh? 8? No, I'm speaking about this.
4.
Not correct. Nothing cancels because everything with plus. 6? Not too much. Something between 4 and 6. di dj of s here. AI, this is a matrix we apply to the vector, yes? AI dj, okay, very good. Now, if you apply this thing to that thing, you will obtain two summons, because this is a product. di of aj, so this is a... Huh?
You didn't say to apply Leibniz.
No, I said expand everything. How many summons? Oh, I have many places to write. Okay, minus blah blah blah. What is blah blah blah? Blah 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 is the same thing, but you interchange ing. So what are the summons which will disappear? Because with minus we will have the same with reverse, so it goes out. This one and this one. You will have the same pair of summons, but with minus sign in the thing which I denoted by this. So this goes out. What is left? We have left the following thing: di of ij minus dj of ai times s plus commutator of these two matrices applied to S. Okay, this is a very nice expression, but I want to make it much more simpler. So as I told you, this guy is a differential form. I calculated this differential form on a pair of basic vector fields. If I want to restore this form, what I'm writing? I write the following expression. So the curvature has two forms. As you can see here, the section can be put outside. So we obtained an operator because there is no differentiation with respect to s, so we can forget about s. And we write the sum over I smaller than j of di aj minus dj ai plus ai aj, and here we add dxi dxj. Okay? People write this formula in some other way. I will write here. People write it as this expression dA plus A veg A. Let us check that this is correct. What happens if you write dA? Look here and write dA. dA is equal. So you first of all you take derivative of this guy. So you write dj of A I dx xj veg dxi. And you take a sum over all I and j. The question, does this thing coincide with the first summoned here or not?
Yes, it does, because the wedge is exclusively.
Yes, because if you keep summons here where the j is smaller than I, you will obtain this summoned, up to changing the notation for indices. And if you look for some other summons where j is greater than I, then you need to interchange and you will obtain second part of the sum here. So this is okay. What is written here? AI dxi veg ij dxj, and we take a sum over all I and j. What happens here? These are matrices. These are differentials. So you will not interchange the order of AI and AJ because matrices do not commute. Well, if you look for sum where I is smaller than j, then you will obtain first part of the commutator. If you look for the summons where this index is greater than j, you will obtain second part of the commutator. So this is a, you can think that it's a complicated sum, but it is written in a very simple form. So if you want to think only about principal bundle, and you don't want to think about vector bundles, you can do the following. You can define curvature on principal bundle by this formula where A on in different charts are related by corresponding formula, and then define F to be given by this thing. The question is, what is the rule? Well, so this calculation was done in local charts. I forgot to say that it was, since I'm writing this thing, calculations are made in local charts. So to be honest, I need to add here sign, which means that you consider local chart, something like this. So in chart alpha, you write this formula. In chart beta, you write another formula. The question is how curvatures are related in different charts. It will be your exercise. Check. That f beta is equal to g beta alpha f alpha g beta alpha minus 1. We have a bunch of undiscussed problems for Friday, but I will add a couple of them. So this is a statement about relation between curvature forms on the intersection of two trivializing charts. Is it clear? Nothing difficult. Okay, let's go on. I want to define a couple of operations. And then we will discuss Chern-Weil theorem. Assume we have K form with values and in endomorphism of vector bundle E. And I have L form with values and endomorphisms of the vector bundle E. And I want to define differential form of this type. Typical element here, maybe in local charts, will look as follows. What is written here? Okay, object here will look like this. And now I want to construct a map from this object to that object. Very simple. You take wedge product of the forms and you take composition of two operators. Nothing interesting. Well, now I want to... Oh, well, exercise with start. Difficult exercise. Very good. Let me define derivative, differential. I'm not sure we will be able to solve it, but nevertheless, let's try. So assume we have a couple of connections. Nabla and Nabla 1. This has connection form A, this one has connection form A1. Difference between them, A1 minus A, is one form with values in endomorphisms of the vector bundle E. What I want to do, I want to check what is the difference between curvatures of this form and that form. This is a kind of exercise because I will not use it. I will use some other formula to relate to curvatures. But nevertheless, it's interesting. Curvature of connection Nabla 1 is curvature of connection Nabla plus very interesting expression D Nabla applied to B plus B wedge with B. So, oh well, this operation is wedge. So we wrote the similar formula for A wedge A. We wrote exactly the same. Well, let me define D Nabla. Differential form, and then we write here an operator T. We act in a usual way. So we apply Leibniz rule here, d omega. That's very simple. But what happens further? Minus 1 to the grading of omega. Now we need to take a derivative of operator. But operator is in terms of connection form Nabla. So we write the following thing. Omega tensor identity on E. So we are here. So we have differential form and endomorphism of E. So I take this object, omega, and identical endomorphism. I do nothing in this term. But now I need to take a derivative of T. the derivative of t is connection form defines connection on this vector bundle. So it's not nabla itself, it is connection defined by nabla here, tensored with connection nabla tilde here. Well, this is an exercise. We start to check this formula. It's not an easy exercise. It needs many calculations. I don't want to do it by myself on the blackboard. It is sufficiently long. But you can try. We will deal with K forms on trivializing chart, tensor with algebra Lie. So this operation will be applied to the following objects: to connection form and to curvature form. So the objects in local chart looks as follows. You have a differential form in trivializing chart on the base manifold, tensored with Lie group G. Then you have another thing. And we construct differential form of this degree tensored with G. So obviously the formula should look as follows. So by which letter I denoted element, okay, S. How to define commutator of these things? In a very simple way. You take a wedge product of forms and take commutator here. For some cases, then your Lie algebra is matrix Lie algebra. You have very simple formula for the commutator, explicit formula for the commutator. Then St is equal to St minus Ts. Now you will see very, very strange formula. So let me write it here. So curvature is given by dA plus A wedge A. So this is an operation which was defined on the blackboard -1, which was just erased. But now we have another operation. And now, if you sit in a local chart, you can add here alpha. This guy became object of such nature. With value, Lie algebra will be matrix. Then people write the following formula: dA alpha plus 1/2 of A alpha commutator with itself. Don't be scared. Commutator A alpha with itself is not 0 because A alpha is a matrix, collection of matrices, so it does not commute. It doesn't. Well, but nevertheless, what we can do. Let us understand why these two things are the same. Let me try to explain. If A and B belong to omega 1 of U, then commutator of AB is equal to A wedge B plus B wedge A. This is explanation. And now we try to understand why this happens. I will try to do it. So let me calculate. Okay, it's too small, yes? Zhenya? Too small?
Yes.
Okay, sorry. Let me calculate commutator in explicit way. this commutator. So what happens? I write here wedge product. And then we take commutator of matrices. Okay, now let us consider wedge product of these two one forms. This is quite simple. The same AI bj dxi dxj. The sum goes over all indices, so no problem. And if you write b wedge a, you will see bjai. Maybe I will change indices and write it in this way. Okay. No, it's not very good, so I should return. Yes. So we have three expressions. Commutator, one wedge product, and another wedge product. And I claim that there is a formula which relates these these three things. Let us check that it's true. Look here. This object, this commutator, consists of two sums. Then you take a wedge product of differentials and the first term in the sum. I claim that that is exactly this one. And this one is exactly this one. Because you need to change the order of differentials here, and they are responsible for that minus. Quite surprising. Commutator of A and B is, because it's graded commutator. It's not genuine commutator, it's graded commutator. Okay, we have new operation. How to calculate commutator of differential forms with values in the Lie algebra. We can write the formula of such type for matrix valued forms, because if we speak about situation then G is some abstract Lie algebra, then there is no product of such type, A by B. No product. You have only commutator. But for matrix Lie algebras, you have the and product and commutator. And they are related by this formula. Very good. So it's time to do something interesting. Okay, let me erase everything, and we pass to definition of characteristic classes by curvature and the notion of invariant polynomial. Okay, let it be complex numbers. Assume that this guy is k-linear. It is linear in each term. Then you can define something like that. P of g is equal to P of, and you substitute the same element here. My question is, what can you say me about what is P of one letter G from point of view of algebra, general algebra? What is it?
Well, there's a thing called polarization.
No, polarization if you go in reverse direction. If you restore, we will write the formula. So I want to say that this is not a sine or cosine or exponent. It's just polynomial of entries of the matrix G. Yes, it's just polynomial of degree k. Maybe homogeneous polynomial of degree k. Now we want to consider polynomials of the following nature. P is symmetric. and secondly, P is add invariant. What does it mean? It means the following. If you let me change the letter here to B. I don't, because G is an element of the group. So let me write here B. B belongs to the Lie algebra. So if you apply add capital at each place, then nothing happens. So you take a polynomial and you apply conjugation by element of the Lie group in each place, and the value of the polynomial should be not changed. That means that the polynomial is add invariant.
Are we working with matrix Lie groups?
I already wrote about it. Matrix Lie groups. Because there are two main examples, orthogonal and unitary. A little bit later it will be spin group, but okay, spin Lie group is the same as orthogonal, it's the same. So we have this situation, okay? Okay, examples of invariant polynomials. If it is one thing, what is the simplest polynomial on one variable?
X.
Hmm?
I guess.
0. Yes, correct. Trace of B. It's symmetric because there is only one argument. You don't need to interchange order. And trace is, it doesn't change its value if you take a conjugation of. There are some other examples, but let me skip it. Sorry? What is written here? Its explanation, trace. It is the explanation why this is an example of what we want to do. Do you know another example of add invariant polynomial?
So it's
Determinant also. But what is interesting? Determinant, we know how to define determinant of one variable, yes. It is a polynomial of degree of some high degree, which is equal to the size of the matrix B. But I defined polynomial as a linear polynomial in each argument. So the question is how to restore the function of many variables, which gives you this one. Sum? Wedge product.
No, not wedge product.
I think, but maybe I'm wrong. Maybe I'm wrong. You take if you substitute their operator B, one operator B, instead of all B1, B2, blah, 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 you will obtain matrix. Oh, well, you will obtain matrix, not a number. What to do?
You can take a trace.
Take a trace. I believe if you take a trace, you will obtain, it should depend on the size of matrix. Actually, there is a polarizing identity. I will write it here. So if you want to know the value of this thing, it can be calculated in this way. 1 over k factorial. Then you take a bunch of derivatives. T1, dtk of what? You substitute here one single matrix which takes into account all these matrices. So you write T1, B1 plus T2, B2, blah, 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 plus TK, BK. That's all. This is a polarizing identity, and maybe we can write it as just another exercise. Well,
So you mean this identity is true for all polynomials satisfied with symmetry and invariance?
yes. So we will use symmetric and invariant polynomials, substituting inside one argument on each place. Namely, this will be curvature. We will substitute curvature here. But if you want to restore polynomial on each variable independently to obtain this expression, you can use this formula. But you need to know the degree of the polynomial. You need to know how many b you have inside, because it contains k. Well, so let me prove lemma. Do I want to have a lemma? Yes, I want to have a lemma. Assume we have b, b1, blah, 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 bk from the Lie algebra G. And also we have add invariant symmetric polynomial of degree k. So I claim that we have the following identity: b commutator with b1. Then we do not change other arguments. Then we write second term. b1 is not touched, and we take a commutator with b2. And do not apply commutators to other things. Plus, and the last summand, as you can guess, is the commutator, bk. Okay, the statement of the lemma is that it is equal to something. This is a cumbersome expression. I take a small break for you to fix it, because we need it. And while you are writing, please think about the proof. And also please think about the statement, because I didn't wrote what is on the right-hand side.
I guess we're going to apply it and then differentiate it to get commutators.
Yes, this is a proof. But what is in the right-hand side of equality? 0, yes. The proof is as follows.
So before you erase, I want to know that P is at invariant if and only if its polarization is at invariant. So we need to check. Well, you gave the polarization formula, but add invariance is needed to be checked only one instance of P, either multivariable or.
Well, so this is a definition of add invariant polynomial. But I think that you can check add invariance here.
Yes, that's what I asked.
Yes, I think so. If we look, well, how to prove this equality? In very simple way. Look here. This is a definition of add invariance. Apply this formula for g, which is equal to exponent of tb. So in each occurrence of g, we have an exponent. And exponent with minus tb. What happens if you differentiate it with that? Then take a derivative d over dt and substitute t equal to 0. And these commutators will become, this add capital became commutator, but one single expression after taking derivative became a long sum which contains many summands. One for this, one for that, and so on. Then you substitute t equal to 0 and you obtain this one. So this is a very simple formula, but very big. Well, and now final step of preparation. So let K be is a C algebra. Let me repeat. You have a question? No. Let me repeat. I already told you that I want to substitute here curvature form. Yes? Form, okay, curvature is but curvature is, what is curvature? It's a matrix, okay, we can think that it is a matrix, it's okay, but it's matrix with added differential, it's object of some algebra. So assume K is a algebra over C, and I want to consider polynomial in more complicated form. So to expand the definition for these arguments. The tensor product is taken over the field which we have, but interesting part is that then people substitute here not curvature itself, but with some normalizing term, something like I over 2 pi. So that's why we write here that values I and C. So argument will look like this one, Ki tensor Bi. Then we calculate pi of such a collection of objects, then we write we put k's in front of everything. Okay. It's not good to write kk. L. And then we calculate P of B1, blah, 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 B. Okay. Very good. Now, I have a question. We will consider, for K, algebra of differential form on trivializing chart U. So it's graded commutative. Until I write something like this, I do not need to think about the order of terms, yes? I wrote it in the order which they appear here. Yes, but if I write commutator inside, I will need to look for the order. So the question will be as follows. Assume I apply what I want to write here, f1, fj minus 1. Here is commutator with a, and here with fj plus 1. And assume that fj is omega j bj, and also a is omega b. What I want to understand, how to calculate this thing.
Well, you omit the tensor product sign.
Okay. Corrected. So the question is, I wrote this complicated expression. Inside fj is two form on the trivializing chart. A is something. I do not actually a will be one form, but now it's not important. So my question is how to calculate this thing. Very simple. Look here. Omega 1 goes from here. Omega 2 goes from here. But then I arrive at this place, I will experience some difficulties because in one order they are written in one way, in another order. But I asked f to be even form. Yes, so if you interchange something with even form, no sign appear. That's why I write the very simple formula here. Then we have b1 blah blah blah, a commutator with bj blah 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 bk. So my claim is if f is even form and a is some form, then you do not worry about signs at all, because then you need to commute something with f, then nothing happens. You can commute it in very simple, because
There
if
should be wedge signs between.
where? Yes, sure. Thank you very much. Sure. Now, you see lemma. Now I have b. So I will write the same lemma, but new. Let me write new, no sign, but the same lemma, more or less same statement, but objects here will belong to not this algebra, but to differential forms. So f1, fk belong to two forms with value in Lie algebra G, and A will be some differential form with values in G. And still we have the same formula, that polynomial P sum is taken over G. So at some place we take a commutator of A with Fg and Fk. And this sum will be 0. So this is the statement which I need finally on the preparation step. Let me repeat. Okay, everything here are differential forms. Then you try to interchange something, there are some signs appear, and formula will be incorrect because some signs should appear in this place, but since f are even dimensional form, nothing happens, no signs. So this formula is the same formula which was written here 1 minute ago. Okay? Okay, let's go. Let me erase here. And now I will give you a statement of Chern-Weil theorem. Let me keep the formula here. The statement is as follows. E so we have a vector bundle with a structure group G, or you can think about principal bundle. A is a connection. P is an invariant symmetric polynomial on G. Then the claim is as follows. What we wrote here, F alpha is a curvature form which sits on the trivializing chart U alpha. If you calculate this thing, you will obtain a differential form. Okay, guess what is the degree of this form? Very difficult question. How to understand the degree? 2k, because you have curvature on each place, and there are k places. If you put them outside, you repeat degree 2 k times. So this is k form over uk with no Lie algebra appear now, because value of this thing is a number. So it's just 2k form, and no Lie algebra here appears. So the claim is it is a global form. It means that Pf alpha coincides with Pf beta on intersections which are non-empty. Second claim is that Pf is closed form. So differential of this thing is 0. And second, there is a class in the Theorem cohomology. So, the very stupid question, the Theorem cohomology of what? Base. Because U alpha is a charts on that base manifold. We have a collection of form which define global form on the base. Oh, well, guess what is the third statement? Imagine somebody take a vector bundle, then he takes connection, then he calculates curvature, substitutes it into some polynomial, and then he is happy because he obtained class and cohomology. He is very happy. But something will. If something happens, he will not be happy.
It's invariant on something.
Invariant on something?
Well,
G doesn't act on E, so
No, there are no G action. It's based. So he will be absolutely happy if this class does not depend on the connection. It's important thing. PF defined by connection A, difference between them, and PF defined for connection A prime is is D of something. It means that in cohomology class defined by connection A and cohomology class defined by connection A prime are the same. It means very interesting thing. By means of differential geometry, we obtained cohomological invariant of the bundle itself. So we started from it's topological objects because it's vector bundle. Then we take connection, then we speak about differential geometry, we took curvature, then we do bunch of differential geometry, then we calculate this thing, blah, blah, blah. Then we defined cohomology class, and since this cohomology class does not depend on our action in differential geometry, then we're absolutely happy because these two classes coincide.
the number of arguments of Pk is our choice.
It's a very good question, because next problem, which we will be solving, it is how to describe the collection of all ad-invariant symmetric polynomials for this particular choice of the group G. Because if the group G is not very good, then you will obtain very strange collection of symmetric polynomials that you will not be happy. But if you took unitary group, the collection of symmetric polynomials is very, very simple. It's just polynomial ring on some specific generators. These generators give you Chern classes. And if you look for orthogonal group, special orthogonal group, then you will obtain a little bit more difficult, but still very nice algebra of invariant polynomials. This will be Pontryagin classes and sometimes Euler class. It depends on the dimension. That's all. Okay, let's continue and prove it. How to check that this is a global form? The proof for this thing is very simple, because look here, f beta is just add capital f beta in some other chart is calculated by this formula. It's just add capital of this. So if you calculate this thing, you need to, on the intersection for sure, g beta alpha of f alpha, g beta alpha minus 1. And since this thing is add invariant, oh, sorry, f alpha. That's all. So we obtain a global form. Very good. So now we discuss. Second statement. I need to erase. Well, I forgot to give you one exercise, very important one, because I needed to use exercise. If you calculate curvature or differential of the curvature form, it will be very simple. it satisfies this formula. You need to check this formula and pay attention to signs and 1/2. Okay, so now we calculate df, d of p of f. To be careful, I need to write that I want to calculate d of multilinear form with f's on each place. Yes, there are k arguments here. Since it is multilinear in each, then you can apply a kind of Leibniz rule. So I write something like this: df, then plus I guess some people from in this room very are familiar with homological algebra. Are you happy with these two summands? Why? No, I differentiate linear form. Sorry? No bar construction. The problem is that differential has degree 1. And if you put it through some letters, you need to add sign. But we are very lucky because f is of dimension 2. You can interchange it with anything you want, nothing happens. So this thing contains -1 to the power of 1 by 2. Nothing happens. So everywhere we have pluses. Now we have global minus, and we write here, by Bianchi identity, we write this formula. Plus P F commutator with A F F, and last one is will you tell me, what do you think about this expression? Why? Because of lemma. Which one? Lemma nu. The last lemma which was written here. So by Bianchi identity, lemma nu, we see that this thing is 0. So this form is closed. That means the differential of this thing is 0. Very good, very nice. Now we need to check that if we have two different connections, then these two forms are cohomologous. So the difference between them is a differential of something. It's not very pleasant exercise to write it on the blackboard, but I will try. So please finish, and then we pass to the difficult part of this lecture. It is difficult not in question of understanding what happens. It's difficult to write on the blackboard, but I will try. So next topic will be the following. We need to understand the properties of these cohomology classes we just introduced, and then to understand what are the nice examples. So we have two connections, A0, A1. Connections. Difference between them is one form. now we define connection of such type. We take H0 and we add here T by C. It is a path in the space of connections which starts in one connection and finishes in another connection. Now we have a P of T. It will be differential form, which is defined as P of F of A T, curvature of this thing. Okay? So what I want to understand that P1 minus P0 is the differential of something. I want to explain what is this something. What happens? I take invariant polynomial and substitute here curvature of intermediate connection, something in between. And on the last place, I put C alpha, difference between with these two forms. It is written in local chart. It's important. The question is, what is the degree of this form? The degree of this form. Let us calculate. How many arguments do we have here? K minus 1 times we have F, and 1 time we have C. The degree of F is 2. And the degree of C is 1. So the degree of 2K minus 1. So 2K minus 1, Theorem differential, 2K, and 2K here. So degree coincides. Okay. Next question. What happens to this object if we pass from chart alpha to chart beta? Very tricky question. These things will be changed by a joint representation. F beta is equal to G beta alpha, F alpha, G beta alpha, minus 1. But what happens to C? C is the difference of two connections. And connection is changed by very complicated formula. No one likes it.
Yes, but the least likable part gets cancelled and we are left with adjoint.
Yes, because there is a joint representation and some constant term which depends on not on connection but on change coordinates. So this guy is still changed by a joint representation. This G beta alpha times G beta alpha minus 1 cancels out because you have one in this connection and another one in this connection. They go out, they cancel. So we have this. It means that it's a global form because it is doesn't change. It changes doesn't change under a joint representation because P is that invariant. So T is a global form. So what I want to do, I want to check that this is true by direct computation. So let's go. P1 minus P2 by what is the name of this formula? Yes, you still remember calculus. Very good. Now, we take derivative at each place, yes? At each place. And since this guy is symmetric, we can write the following thing. That is k. We will have k equal summons. And on the last place, we will see df t over t. Yes? What I want to do, I want to calculate this expression. It should not be very difficult, but I need to calculate it. Okay, so I erase on the right-hand side, and let's go to... What is ft? So I take d of a0 plus tc plus a0 plus tc. Am I writing with commutator or not? I'm writing with commutator, okay. How many, oh, so standard question, how many summons do I have here? So how many summons? 6. No Leibniz rule. 2 here and 4 here. If we take A0 only, we will obtain what? F0. Yes? Yes. Now let us look what happens if we look at coefficient at t. 1t is here. So dc. Another couple of t's are here. c by a0 and a0 by surprise is here, in this place. In this place you have a surprise, because A0 by C, C by A0, and both with a multiple 1/2. Yes, but it is graded commutator. It's symmetric, not skew-symmetric, but symmetric. So they not cancels, but they amplify one another. So this is a commutator without 1/2. Now we can say what is ft over dt. It is just dc plus a0c plus t okay. What can you say me about this term? Hmm?
0.
No, it is matrices. The surprise is here. This is dc plus commutator of at with c, because these two terms gives you this one. Then I was preparing, I had the hope that this guy cancels, but not. They together give you this one. So we can continue this calculation. And on the last place, you will see dc plus commutator AT with C. DT. Very good. So we are almost finished. Please fixed until this point, and then we will calculate differential of this stuff. So we have left-hand side and right-hand side. Left-hand side is simplified until this expression. Now I will simplify this expression, and I will hope the result will coincide. Maybe not. Then you will have an exercise. So where is the formula for this guy? Well, please be careful, because I wrote this formula in local charts, yes? In local charts, so...
You've got the differential in front of it.
Sorry? Yes, I forgot differential, df. In local chart, but no alpha index for simplicity. Same applies here, because we did this calculation also in local charts. Okay, so actually, you see, we see k here, we see integral, so we need to pay attention only expression which is under integral. So let us calculate this thing. It's quite stupid. Look here. This is multilinear thing. We take a derivative, so we apply Leibniz rule. So it looks like this: dft, ft, ft, c, plus dft c, and plus ft, blah, 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 ft. Now we have dc. Okay? How to calculate differential of f? Bianchi identity. Bianchi identity. So dft is equal minus commutator with at and f. Very good. So we have minus commutator on the first place, minus blah 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 minus f. We are almost finished. Don't worry, a couple of lines. Please pay attention. We have commutators on each place except last one. It's crucial because we need to calculate differentials of curvature forms. We have k minus 1 of them, so we have only k minus 1 summoned here. Plus we have a bunch of summons. And we know that it is almost 0. Because if you have this migrating commutator, with moving commutator from one place to last place, the sum will be 0. But here we have all summons except only one. So we can replace everything which is written in the first line by only one summand, which is a completion to this thing to be 0. What is it? ft, blah, 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 ft, commutator at with c. So this summand with all the summands in this line together will give 0 by Lemma nu. Plus p of ft, ft, and dc. Miracle. So the theorem is proved. Very good. So now we know the following idea. So if we have vector bundle, then we can construct for this vector for vector bundle and add invariant symmetric polynomial, we construct a characteristic class, some object. So if we have pair vector bundle and polynomial p, this data gives you class in H star of the base. Yes? This is assignment. You have a vector bundle, you have an invariant polynomial, then you obtain class and cohomology of the base. This is a very simple part of the idea of characteristic class of the bundle. We will discuss it on next Tuesday. What is a characteristic class? And then we should discuss how many classes we will obtain in this way, and that's why we need to understand how many invariant polynomials we can construct in a simple way. Well, so this is all for today. Thank you very much.